다음 저널클럽 연사님은 SQRT의 오세현님이십니다. 오세현님은 서울대학교 물리천문학부 물리학 전공을 하고 계시며 서울대학교 강민구 교수님 QMS 그룹에 소속되어 계십니다. 관심 분야는 카곰의 PRXD, XRD, ARPS, PR Reflexity, 그리고 Charge Density Wave입니다. 오늘은 Charge Order Melting Dynamics of 4d-kogome Metal, 요거는 읽는 방법을 제가 모르겠습니다. 에 대해서 소개를 해주실 예정입니다. 그러면은 오세현님을 큰 박수로 맞아주시길 부탁드리겠습니다.
Hi, my name is Sam, and I'm from Swedish University, Department of Physics and Astronomy. And today I'm going to talk about the charge order melting dynamics of lutetium-19, which is a very recent material, which has a few papers about it. And I think you might be unfamiliar with the quantum material and like Kagome or time result XRD or the accelerator physics. So, and also it is the quantum information session. So please be open-minded about it because I think the quantum material study will give a very good platform to the quantum hardware. So it might be potential of your hardware system, and also it is very physically interesting. So please, okay, okay, okay. Please, please make many questions. Okay, okay. This is my resume, and yeah, I have very many internships, and they're all about the artists. And now I recently focused on the XRD study, which the facility is in Pohang, the linear the accelerator system. So so my interest is time result ARPS. ARPS is the spectroscope that can observe the band structure of the material, and also is and time result XRD, which gives dynamic evolution of the structure, and also time result reflectivity, which will omit this session. So today I'll focus on the time result XRD, and this paper is about it. So I know you're all new to the Kagome, so this is the Kagome lattice. And you'll see there's a Star of David inside at the center of the lattice. And yeah, it is. Oh, I think the slide is missed. So the Kagome lattice is a kind of a next generation of the graphene. The graphene is made of two bases atom, and each atom is forming the triangular lattice. And the common lattice is formed of three bases of atoms that have forming the triangle lattice. And you'll see that it is quite not really conventional because graphene is bipartite lattice, which gives non-frustrated geometry when you think of the Ising model. But if you think the Kagome as Ising model, then there is no clear picture of the ground state in the Ising model. So this is geometrically gives the frustrated physics. So it is very interesting in when it becomes a magnetic material. But also the lattice as a geometry, it gives three interesting band singularity called the Dirac points, quantum singularity, and flat bands. You might know that the graphene shows the Dirac points and quantum singularity, but they're showing flat bands when they put the Morris structure. But the Kagome lattice, you don't need to put additional lattice and take the rotation. It gives flat band as a pure state, in this lattice structure. So think about the wave function that is enclosing the hexagonal in the center, like shown in this screen. And you'll see that the plus sign is alternating and minus is alternating. And if you think of the hopping process at the top of the 2 points of the hexagonal, the plus and minus, to the upper sides, there's one up in there. So the electron hopping from the plus will give the plus sign at the side, and minus sign will give the minus sign. And you might know that the quantum mechanics, that it is just the mathematical addition of this two wave function to give the new wave function at the side. And what is become plus one minus one? It is equal to 0. So there is no hopping outside of the center hexagon, which means the electron is highly localized in the hexagon. And when the electron is highly localized in each of the hexagons, then it gives a highly periodic structure. And you might think of the Fourier transform, then the highly periodic structure will give you a constant, which means the black band. So black band is very basic to this total lattice. There's several interesting points about this lattice, but I will omit this. So this is the Pollax film, the fourth generation. Yeah.
The greatest lattice of the Kaplan lattice.
Sorry.
What is the greatest lattice?
Bravo lattice.
Yeah, basis pair.
Base vector. Yeah, it's just the triangle lattice.
Triangle.
Yeah. Just look at the small triangle. Each of the corner is the basis, and there is a translation vector in the upper side and the horizontal side. Then you can think there is, yeah.
So it's 3 is not basis, not 2.
Yeah, 3.
3, not 2.
You're right. Yeah.
So that's why there is like directions and flags.
Yeah, right. That's right.
Okay.
So the German columns in Vowel singularity, as you commented, it is inherited from the Grafton structure, and the Grafton structure is made of two triangle lattice bases, right? So this is the accelerator facility that I used last summer and 2 weeks ago, and this is the infra inside the beamline, and I was participated as a main contributor. So there's also new concept about you might not know this. It is XRD. So actually, simply you can think of the Bragg condition in the high school physics text that if you put some X-rays in the sample, and the sample will react to the X-rays by as a quantum oscillation inside its structure. So if the condition matches with the inference condition, then it will give a high spots in the 3D sphere, and that is called the L sphere in this XRD spectroscopy. And I'm looking for there is some interesting spots around the L sphere and see the time evolution of this peak. So XRD gives a lattice information using the Bragg laws, and the types of XRD it gives the time resolution, and it gives the structural dynamics of the material. So the Kagome lattice is very rich in the nature because there is very many material that we know the structure, and the 4%, which is very high portion of the total, is the Kagome. So Kagome research is very hot in this era. And yeah, I said there's a three-point singularity. And also you can substitute the atoms, like the transition atoms, for like for 40 atoms. So you can put any atoms in the Kagome family, and you can make a gradual series, the Kagome series. So when the direct point is getting to rest, when the firm levels is inside the dark cone, then there is the anomalous Hall effect shown in this material. And when the boundary singularity is on the firm level, then you will see the firm surface nesting during short density wave. And also, when the flat band is on the Fermi level, then there is kind of the quantum mechanical effect that gives the splitting of the upspin and downstream lap band, and it will give the very small gap inducing the non-fermi liquid phases. So there is a very rich phenomenon in this material. And today I'm going to talk about the charge order, the charge density wave. So what is charge density wave? It is the charge density redistribution. It is the base formed by the redistribution of the charge density, and that following not the lattice periodicity. You can see the figure. The common lattice is colored as white, and the green is the redistributed charge density. So you will see that the charge density forms a supercell, not following the lattice periodicity. So, and this charge-density wave is very normal in the nature. So if you lower the temperature, then you'll see charge-density wave in many material. And also, it is originated from the two major origins called the Fermi surface nesting and electron photon coupling. So, for example, the cesium Banach antimony, the bottom chain is Kagome, and this CW is driven by the electron origin. And also the scandium is driven by structural origin. So this is the major CW common materials in recent 5 years. The cesium antimony is shown in the lab figure, and you will see that the carbon lattice is surrounded by the scaffold of the cesium, and the cesium is very hard and high mass, so it is not moving. So the origin of this metric, the CW, is the movement of the in-plane components of the carbonate, and you will see it in the next figure. And also there is this kind of a T, which is recently reported like 2022. And there is the scaffold, but it's not really messy. So the major goal of the CW is the movement of the scaffold in the on-plane direction. And also there's a ion germanium, there's a bipartite material. And this material has magnetic components from the ion. And this ion forming an antiferromagnetic coupling inside the interlayer AFM coupling. So the magnetic energy is the major goal of driven charge density wave. So this kind of origin is differentiated from the spectroscopy, the ARCAS, the isotope, and the time X-ray and time tunnel. So this is a very typical figure of the charge density mounting dynamics. If you put the X-ray in the material and observing observing the charge density wave peak, and you will see the intensity of the charge density is decreased because if you put the X-ray, then the charge density wave structure is melted. It means distorted, and it recovers back because the temperature is below the TC. So when it recovers back to the original charge density wave structure, then it gives the current photonal oscillation called AO modes, and the atomic distortion is moving up and down and come back to the original intensity. And in this region, you'll see the current oscillation there. So by analyzing this frequency, and you will see which is the driving force of this charge density wave. So in this paper, they talk about the charge density wave is originated from the carbon lattice breeding. So you see this left upper figure, that there is two major phonons in this system. The first is M phonon in the A figure and L phonon in the E figure. And if you think of the 3D structure of this photon mass in like stacking the M phonon first, L phonon, then you'll see the MLL phases in the C figure, which gives kind of hexagon and a localized triangle phases that is alternating in the stacking order. And also you think of the LLM phonons as stacking in 3, then you'll see the LLM phase, which gives the like a star shape and a kind of phase shifted star shape in the lower layer. And this kind of 2x2x2 supercell is the charge density wave in this antimony material. if you put the pump in this material, then the first phase, in the E sphere, the first phase autopilot is going down, but less, and the second autopilot is going down much larger. So the dominant CW in the pump experiment is the phase number one. It is MLL phase. So this temporal can see which CW is more stable when you put the not unstable phases, like if you put the pump in the material. Yes.
So you're saying that there are some metastable phases when you like pump in the X-rays?
Yeah, not this material because this material shows only one energetically and experimentally stable CW in the system. But in the following system, the Spider-Man team will show the metastable states in this three-energy landscape. So I'll talk about it.
And what's the major frequency of the charge density wave, like the period in which the density distribution recovers after the curvature?
So you mean the numerical value or
Yeah, the numerical.
yeah, it's just kind of terahertz. Yeah, yeah, 1 terahertz and between 5 terahertz. So it's typically around the 1 to 2. So I'm gonna talk about this paper. It's very long journey, but it might be very interesting. So there is no difference in the state role when you look at the charge density wave in Scandinavian and ion germanium. But there is definite difference because ion germanium shows an AFM coupling. So when does the AFM coupling does role in the spectroscopy? It is not in the static spectroscopy, but it is in the time result XRD, the time result spectroscopy. So time domain gives the decoding of these two phases, the ion germanium and standard gene. Let's see the charge density wave melting dynamics data here. The first schematic shows the ultrafast melting is around 200 microseconds, and it recalls back to the original intensity with the current bonus. And as you put the equivalence higher, then the amplitude mode frequency will lower. Why this is happening? It can be explained in the consistent way. I'll show you later. And also, the same experiment had done in ion germanium, but you see that there's no ultra melting. There's no melting in the sub-picoseconds. And if you put the longer, then there is only thermal effects, which means that if you put the high influence on the material, then the electric temperature will rise up, and the lattice temperature will rise up locally, and so there is a lattice expansion, and the expansion of the lattice will result in the shortage of the peak in the reciprocal space. So the peak is moved. So we are looking at the points, a detector. So the peak is moved, then it's effectively showing like decrease of the intensity.
So the temperature is the lattice temperature, not the electron.
It is hard to say because fluence gives the electron temperature, while the lattice temperature is driven by the sample stage, the cold finger. But in this kind of small sub-picosecond region, then the two temperature will split into two, and they converge into one after just maybe 200 picoseconds. So in this region, there's a temperature difference.
So the temperature we written in the graph is the lattice temperature, like 40 Kelvin, 100 Kelvin.
Yeah, right. It is lattice temperature.
While the electron temperature stays at maybe 40 Kelvin.
Yeah, right. You're right.
Okay.
So there is not much of charge density wave-driven current oscillation. Why this happening? So here's the answer. If you calculate the DMPT, which gives the Florin distribution of the material, then the scanning shows very imaginary components around the gamma to A direction. And there's the major instability at L, which gives the L Florin. And if you, the metric tries to resolve this instability by forming the charge density wave. So it's phonon-driven signal wave. And if you interpolate the charge density superstructure with the pristine structure and calculating the free energy by DFT, and you'll get the second figure there, and it shows the double web potential. And the order parameter is the distortion from the pristine to the charge density wave. So order parameter shows at onset at one. The one is the CW structure. And if you like put the X-ray and give the fluence on the material, then the double structure will rises up, and the order parameter minimum will change. And the change of the order parameter, they try to go back to the ground state at the fluence. But as the time evolves, the temperature will goes down and the free energy density will goes down also. So they're making the oscillation transiently and tapping the minimum, and they come back to the original position. So that is the very clever explanation about the charge density wave melting dynamics. But if you look at the iron Germany, it shows very different regional scheme. And also there's no instability at the form nodes. So it is not form driven CW. That what makes it this triple well free energy. So as same with this Steinway team, it is we can just calculate the elastic energy, the distortion of the atom, and calculating the elastic energy all around the atoms. But if you put the magnetic energy here as some of them, then you will have the three ground state, two ground state, sorry, one ground state and the metastable state at the center. So if you think of the fluence, put the fluence in the material, then there is some point that the zero, the pristine structure is the exact ground state at the time. So the order parameter will tap in the center, the pristine structure for a while, and it goes back to the charge density wave structure in the is denoted as 1.0. So also it is not the end. Here is the animation. You'll be familiar. As I explained, the order parameter it rises up as the fluence increases, and there is current oscillation transiently, and it comes back to the original one. But if you look at the ion germanium, because of the magnetic free energy, the minimum of the order parameter is not really changed. So there's no need to movement of the order parameter or the atomic distortion or the current oscillation. So it comes upward and it touches metastable state, and they come back to the original order parameter. So there's no order parameter change in the time domain. So this is why it gives no current oscillation. So my research is started from here, and there is also the CW common material in the similar sister family called LuNb6Sn6. And I want to look at what is the driving force. And before to start, is it really gives the current oscillation in the same experiments in this material? And if it does, then what is the origin? So here's the experimental results. So I measured the left figure, and you will see very different dynamics between the Scandinavian and the they're basically same structure, but the Kagome lattice, it is the 9 Kagome. It has the twice heavier atomic number than the vanadium chain. So the Kagome is more heavier. So this is why the current oscillation, the frequency is overall lower than the standard vanadium. And also there's no kind of the dip at the sub-picosecond region. I don't know why. So we measured 2 weeks ago, and actually we get a different response. So why this happened? Because this is due to the sample damage. So if X-ray is too high, it gets too high fluence, then it'll harm the surface of the material, and the charge density wave is formed underneath the surface. But the X-ray is kind of very strong probe that it gives deep penetration depth. So it can give the signal from the bulk state, but electron is hard to move from it from the inside. So the intensity, so it needs more flux than standard T, and also it has a weak oscillation. So yeah, I'm now processing the data. So here, this is just the old data, but still you can see there is current oscillation as expected. Also, there's an temperature dependence on this data, and this gives that as the temperature increases, the current oscillation is getting, the frequency is getting lower. So this is the great evidence that this is CDW. CDW originated the oscillation because as it comes closer to the TC, the critical temperature of the CW, the current oscillation is removed. So yeah, this oscillation from CW. But in between the experiment, there is also very interesting and very annoying results that comes out that this material is very unexpectedly having the metastable state, which gives kind of second scale recovery components. It is not very conventional in this experiment because the accelerator beamline shows the 60 hertz of X-ray roll. So they put the pulse in between the interval of 16.7 milliseconds each, and the charge wave is damaged, and they recoils back, and they damage, recoils back. They do this iteratively, and they merge the signal to get the current oscillation in the sub-picosecond because the noise level is too high. But in this experiment, it is quite hard because there is a second scale recovery, which means the X-ray should be put in longer than like 14 seconds. So then that'll gives the experiment time elongated quite much. So it is impossible because our beamline was given as only 7 days. So we just experiment and see the long report confidence is onset in this material. So this is a kind of clever setting of the experiment that if you put the X-ray probe in like 60 hertz and laser pump as the 15 hertz, so there's a 4 times larger in the frequency, and you see the on, off one, off two, off three signal. And if there is kind of a long recovery confidence, as shown as the blue curve here, then you will see the gradual increase of the intensity in the signal. It is not it is just manually, not manually done. It is kind of very hardworking. So we get this data and there is gradual change of the intensity. So this is indirect evidence. So the direct evidence will be the solution experiment, the single after the single pulse of laser and showing the response in the time delay with the long range of time. So this is just picosecond scale. So if you look at the second scale recovery, which is also very not in the manual. So we do by clicking very short time, like dot, and we get the signal. And you'll see that there is really 14 kind of 6 seconds of recovery component in this material. So we still don't know why this is happening because when we calculate the DFT and getting the 300 landscape, there's no metastable state here. But the data shows there is a metastable state in this material. So we couldn't resolve this discrepancy with the experiment and the calculation. So this is an open question. But still, there's it is not unusual because there's another material called like cesium bismuth bromium. I don't know, but there is kind of very long recovery components in these materials too. I saw kind of 36 hours of recovery in some material, perovskite material. So in summary, the charge order matching dynamics in Lieutenant 19, it is shown unexpectedly about the evidence of metastable states. But before it, we get the current application model oscillation as is shown in Scandium T. And also, the sequential experiment shows the second state recovery at this point. And and also we brought the another third order peaks around it, and we saw the melting, which means that uh, in the sub-picosecond region, the old observable observable peaks, total peaks are melted, and if you think of the intensity, the total intensity, it should be conserved, which means that there might be another Korean peaks in the respectable sphere will rise up in this region. It is the metastable peak we expecting. So we should find, but we are looking for the another meantime. So the further study on this material will be the result of reflectivity, the enhanced X-ray scattering, and Raman to analyze this phonon dynamics and which phonon is the driving force of this material. So thank you for listening.
How can you experiment with it to distinguish short density waves with thin density waves?
Oh, that is hard to yeah, because we are not dealing with the magnetic material. The scandium and lithium is non-magnetic material. So I haven't think of it, but I think there is kind of mock experiments because it gives the smooth texture information. So I don't know, but that might be the case. But in this time resolved X-ray spectroscopy, there too cannot be discriminated in this technique because it just gives the structure coupled with the other degree of freedom, and it only gives the superstructure as a whole. Any questions?
I have one more question. I believe the intensity of the X-ray was like close to a kilo electron volts, right?
You're right.
Yeah, about 800, 900 electron volts. Does not, isn't that enough to like damage the samples? Like, right there, that's quite high.
So actually, this energy scale would heat the core level of the atom. So, but core level atom does not mean that the atom is damaged. The damaging parameter in the experiment is the height fluence, not the electronic energy. But yeah, I think it is because it is some X-ray region. But if you took it to the hard X-ray region and further, then the electronic energy will harm because will exceed the core level and will damage the chemical characteristic of the cross crystal structure. But around 1K electron volt is not the major factor affecting the damage. So in this experiment, the this crystal is damaged after like 10 millijoule per centimeter square, the fluence. But if you increase the X-ray energy by 1400 electron volts, it is not hard. Yeah, it is kind of just a matter of avoiding the core level of the atom and kind of avoiding damage of the team, damage of the scandium. So yeah, that's all.
So the electron phonon coupling is the force that drives all of this dynamics. Is that what you're suspecting?
The 19.
Yeah.
Yeah, because there is very interesting view from the sample makers that the scandium T then and lutetium T. This family is called 166 material, and this is from the iron team Kogome lattice. So here may be the best image here. So yeah, look at the iron germanium, the lattice in the upper right, and you will see that the scandium vanadium team is very similar to the iron germanium. And this is because the vanadium team in the scandium vanadium team material is forming the iron germanium structure. And you put the transition metal, the scandium, in this material to form the void inside, point between the scaffold here, there in the germanium. You see the void inside the germanium structure, and the resulting structure is here scandium. So by by putting the transition metal inside the void, this pulls out the carbon lattice upward in the upper layer and pull down the carbon layer. They bend the inside the unison, and this gives a kind of structural instability in the C direction. So 1,6 material is in purpose of making C direction phonon instability from the sample maker's view. So it is expected. And as expected, scandium is shown, and the titanium is also shown here.